Hey students, welcome back. We have one more from chapter 16, one more video from chapter 16, and then we have one from 18, and we're going to knock that out right now. This one to me is kind of a more fun one. We have LeChatelier's principle. All right, LeChatelier's principle. All right. LeChatelier's principle basically talks about a disturbance in the equilibrium and which way it'll shift. So we're talking about what happens when there is a disturbance to the equilibrium. All right. Now, real quickly, it's not like a disturbance like, in your neighborhood or something like that. We're talking about a disturbance to the equilibrium that causes the equilibrium to have to shift and kind of figure that out. Okay. So if we look at that, we're kind of just going to jump right in because let's be real, it's easier to kind of see some examples and go from there. So we have this reaction right here. We have N2O4 going to 2NO2. Now, what effect will the following have? So if I add N2O4, that means I have too many reactants, right? If you think about it in terms of reaction quotient, our denominator is too large, so it will have to shift to the right, all right, or shift towards the products to even it out, right? Because currently we have too many reactants, and we need to shift to the products to kind of balance it out. Because remember, we're trying to get back to K every time, right? The same K because K is constant. So now what happens if I add NO2? All right, so now this time I'm adding NO2. What will happen if I add NO2? Well, if I add NO2, I'm having too many products, right? So it's going to shift towards the reactants. All right, and scientists use this to kind of make reactions do what they want it to do and get more products, because there's some reactions that don't yield a lot of products unless you do some of this manipulation. All right, now the next one, not that it's tricky, but let's see if that helps us out, if we can figure it out. So what if we remove some NO2? So this time we lower NO2. Well, our ratio of products to reactants is too small now, right? So it will shift towards the products. All right, we've got to get our ratio the same each time, so it'll shift towards the products. Okay, so that's a fairly straightforward one. Okay, I'll erase my arrow. All right, now what happens when we have like a volume change? All right, so if we decrease the volume, it causes the reaction to shift in the direction that has the fewer moles of gas particles. Why will it shift towards the fewer moles of gas particles when we decrease the volume? If we decrease the volume, we're also increasing the pressure, if we think of it in those terms. So if we're increasing the pressure, it'll shift towards the fewer moles because that'll take up less space, right? Fewer moles of gas take up less space. All right, and so that's why it'll shift towards the fewer moles of gas. So then kind of the opposite is true. If we increase the volume, it'll shift towards the greater number of moles, and that's because it has more space. More space for more moles. Wow, that was rough. All right, we'll try that again. More moles. All right, now if we have an equal number of moles of gas on both sides, there will be no shift. Right, which makes sense. There will be no shift because there will be no benefit for going for fewer moles or for more moles, depending on what we've got. The other one that AP likes to throw in there and kind of add as a little bit of trickery for you is that if you add an inert gas, technically, right, the pressure will increase, but it will have no effect on the equilibrium. All right. And that makes sense because, well, if we could actually take it back to collision theory, right? If we have the collision theory and we're talking about it going back and there's more collisions, but none of them are favorable. So there will be more collisions, but just not what we need. Okay. And the last one, the effective temperature change on equilibrium. So we're going to think of an exothermic reaction as heat with a product. And then if we have an endothermic reaction, we think of heat as a reactant. Okay? Endothermic, heat is a reactant. Exothermic, heat is a product. So let's kind of see how this works. So the following reaction is endothermic. That means we have to add, wasn't on my pen, we have to add heat to get this reaction to go, or it takes in heat, right? We add heat on the reactant side. So what is the effect of increasing the temperature? So if we think of it in terms of that, if we increase the temperature, we have too many reactants, right? So it will shift to the right. So this first one, it'll shift to the right or towards the products. Okay, that's an endothermic reaction. Now, what about if we decrease the temperature? All right, this time we're going to decrease the temperature. Well, it's got to shift to the reactants to make up for that. All right, awesome. Makes sense? Catch you next time.